Imagine, it is a beautiful sunny day in San Francisco, with no sign of fog in the sky. You're planning on finding iced coffee with your friends on your way to hanging out in Golden Gate Park. You search coffee in Google Maps, but get no results. Not only is that a little hard to believe for San Francisco, a city known for its coffee culture, but it's a surprise to the developer team that works on the feature, who page SRE to accelerate rolling out a fix. In the weeks afterwards, business leaders express worry about this user-impacting incident. How could a critical feature break for so many users? How can their teams invest in closing off the risks of similar issues? In this case, solely relying on server-side signals wouldn't allow us to close off risks to users, as there are times when no results are actually expected. Stories like this catalyzed our team's shift towards user-centric monitoring. Before we begin, a bit about me. I'm a tech lead on a team of SREs focused on geo products, like Google Mobile Maps, and I'm a self-confessed map nerd. For context, I'm a member of Reliability On-Call for widely used consumer and developer-facing products, including consumer Google Maps on your phone and the Google Maps Platform API. These services have been around for a while, with many users and use cases. As a result, we have challenges from running global services, as well as complexity from deploying apps to a global user base with a wide variety of operating systems and device capabilities. Over the years, we noticed that server reliability investments like global redundancy and graceful fault handling had really started to pay off. The number of SLO misses our team was paged for was dropping, and users were getting a fairly reliable experience. When we analyzed our postmortems and incidents in a quest to make things even better for our users, we noticed a trend starting to form. Our remaining outages were issues we weren't catching with traditional server-side alerts. These outages were more subtle, where the servers were running well, but the user experience was broken. In many of these cases, it wasn't clear how we'd even catch these incidents with server monitoring. Manually detected incidents escalated by users last longer and are more severe for our customers, emphasizing the importance of our pivot to user-centric monitoring. In the spirit of rising to the challenge, we've also reflected on how AI-powered user experiences have added another layer of complexity on top of the challenges that we've already tackled. I'm now going to talk about the business impact we delivered by solving this problem for our organization. User-detected outages are typically longer and more severe, making them worse than the reliability issues our team responded to before we began our pivot. Outages with external user impact can reduce user trust in our product and impact critical business metrics like engagement, adoption, and retention. To achieve this business impact, we invested in automatic outage prevention and detection capabilities capable of catching bad changes earlier, reducing the number of users impacted by a reliability issue, as well as the length of time they're impacted for. As part of our journey, we've continued shifting detection earlier, preventing any external users from being impacted. The second opportunity I'm going to talk about is reducing the level of effort required to fix reliability issues. Early and automatic detection reduces the level of effort required by our organization, allowing it to focus on its core mission: shipping features that surprise and delight our globally distributed user base. As such, our organization views reducing cost to fix as an opportunity to have outsized impact on the business. The chart here shows my artistic interpretation of the cost for our organization to fixing reliability issues at different stages in the software development lifecycle. Moving from left to right, issues detected during release or before code is submitted can be rolled back easily, translating into low cost to fix. In contrast, production outages require urgent incident response, which disrupts the core work of software delivery. Today, I'll be talking about our organization's journey to user-centric reliability, including the technical capabilities and measurements we use to prevent and detect outages earlier in the software development lifecycle. I'll go deeper on the case study and how it led to an aha moment for our executive sponsors and ourselves. Lastly, I'll share what we learned along this journey, as well as my view on how user-centric reliability will transform how reliability teams operate across the industry. At the beginning of our team's pivot, we began with asking why. We analyzed outages to understand how we could prevent them or catch them faster, and identified two gaps. First, given many outages were caused by some sort of code change or release, we weren't always connecting our change supervision systems to measurements about the user experience. Second, production alerting, which is great for telling us when a server is getting too hot with requests, also didn't capture the full user experience. With these lessons, we began applying our outage prevention and detection capabilities through deep engagements with engineering partners using a three-step process. First, we partnered with owners of core user journeys to align on feature criticality and the potential severity of outages. From there, we began building the technical implementation of signals that would allow us to directly measure the user experience. Lastly, we integrated these signals in a system capable of preventing and detecting outages, which we call defense in depth. When engaging with product teams, we aim to understand which features and their components are the most important. Examples of questions we asked were, what qualifies as a must-have from the user's perspective? If the feature is broken, degraded, or has poor performance, will the user notice? What's the impact of failure? Do we lose revenue, or will users seek out alternative solutions to fulfill their needs? And lastly, what regressions are severe enough that the business will invest concrete resources, specifically incident management, to fix urgently? Next, we translated user expectations into concrete measurements of the user experience. For many of our partnerships, the signals were already developed, but developers were not using them in automated alerts. In other situations, our conversations led to engineering teams investing in building out signals that could feed into automated systems. Borrowing from our experience with the types of issues that we would be on call for with serving systems, we focused on three main types of measurements. First, availability, which captures whether a feature is working at all for a user. Second, latency, which measures the performance of a feature. Previous research shows that milliseconds of delay on critical Google features like search impact how people use the product. And last, data quality, which represents whether the information we return to a user is highly relevant and contains all the results that will let them complete their journeys in Google Maps. We tackled availability first because this failure mode is often obvious to users. When a user clicks on a button, does it take them to the expected destination? We built monitoring using a core dataset that developers add when implementing new features to log impressions and interactions on user interface components, called visual elements, anonymized to protect user privacy. The automated systems we built analyze this data to determine whether a sequence of user interface elements occurs as expected. For example, if a user clicks on the map, they should then see a screen that shows a point of interest. When these if this, then that assertions become broken for many users, we can send automated alerts and feed that signal into our change supervision systems. Next, we focused on latency. One aspect of measuring the user experience is knowing how applications respond when the user performs actions like clicking on a button. Was the experience noticeably slow? If the responsiveness of the app is bad enough, it might be indistinguishable from the feature being broken. The graph on the right shows one type of signal that we use to assess performance, called traces. The image visualizes execution of code in Google Maps using an open source tool called Perfetto that is built into Android. Each color in the graph is associated with timing information on events, like UI rendering, that we can use to calculate an alert on user perceived latency. One added benefit of tracing is debuggability, meaning that we're able to understand why performance has regressed. For example, is the code that actually draws the UI on screen slower? Did someone unintentionally add logic that runs on the main thread when it should run on a background thread? Or have existing network requests gotten slower? Have new ones been added? The last main category of signal we ingest is data quality, which captures aspects of the information returned to users. Many user interfaces in the products we're responsible for are powered by a microservice architecture with downstream dependencies. To prevent a single downstream dependency from causing a major feature to break, we implement graceful degradation. Rather than failing the whole request, we will return a subset of the information that we could have. Examples of this include displaying suboptimal search suggestions, non-personalized results, or not showing features in the view of a point of interest in Google Maps. Data quality is slightly more nuanced than other user experience monitoring, where something is obviously broken for users. Instead, the impact of data quality regressions is a slow boil of shifts in user engagement, adoption, and retention that results from less useful features. To prevent outages from escaping to users, we process the measurements I just talked about, piping them into change supervision mechanisms that pause changes if they're about to trigger an outage. We focused on user-centric automated feedback of 4 types of changes. First, server rollouts, where a new version of server code or configuration is deployed. Second, application binary releases, which involve shipping a new version of a mobile application's code to an app store. This is particularly challenging if there are user-impacting issues, as we can't roll back a released app in the same way we can a server in the cloud. Third, feature ramps, where a new feature is tested with X% of users, and that can cause issues for a subpopulation. And last, data updates, where changes to underlying information, like map data, causes a user-impacting outage. Over time, we aligned pre-production automated feedback with change supervision, shifting detection even earlier, further reducing cost to fix. This allows us to catch many obvious user-impacting outages before any external user is exposed. For example, our organization performs manual QA testing of user interactions on pre-release versions of servers, apps, and feature ramps, which is useful for parts of the user experience that are difficult to test automatically. To scale pre-production testing, we've expanded the suite of automated tests and aligned them with critical user journeys that we're monitoring in production. We've also used AI-enhanced capabilities to generate test code automatically, as well as scale evaluation results, for example, reasoning about screenshots taken during test runs. One insight we had is that change vector supervision was not enough. Occasionally, changes outside of our control have led to user-impacting outages, but we still want to respond to the incident and ensure it is mitigated quickly. As a result, we also use the same user experience measurements in near real-time alerts to monitor beyond the rollout. I'm now going to dive a bit deeper into a case study that demonstrates how impactful these capabilities have been for our organization. Before we embarked on this journey, we were able to defend server-side availability and latency SLOs, but there was sometimes a circuitous route to user impact. For example, a server in the cloud could return a large number of errors, but the impact to users could be minimal due to client retries, graceful feature degradation, and caching. Before we implemented user-centric monitoring for the search experience, there were recurring serious outages every year. After our work, we prevented and detected outages that otherwise would have impacted users. As we've shifted detection earlier, we've prevented these significant outages from escaping. Furthermore, we have a last line of defense in production alerts that page on-callers, meaning that we respond to pages rather than reports from users or Googlers. Additionally, we've connected reliability improvements directly to critical business metrics. For Z results, we were able to quantify the failure mode's impact to user engagement, adoption, and retention. Predictably, users attempting to search in Google Maps would search for other options if the feature wasn't working as intended. Over time, we've integrated user-centric reliability into the delivery of critical features by our organization. At the start of engagement with product teams, new client instrumentation has often uncovered issues. Over time, the better detection mechanisms we've developed have led to the perception of more outages because we were able to catch some very small and subtle issues that might not have been caught otherwise. These outages were also very costly to debug and fix. For Z results, all of these factors led us to kick off a Code Yellow, an event where we immediately form a temporary team to tackle an important issue. A key pillar of this event was integration with change supervision, capable of preventing users from getting unexpected search results. The code yellow was very successful in stopping the no results problem, shifting detection earlier. This was an aha moment for our executive sponsors and ourselves. Going back to the opportunities I cited at the beginning of the talk, shifting left reduced user impact as well as cost to fix, because it was very clear what change caused the problem. This approach has changed how we talk about user-centric reliability. When we're proposing a team to do some reliability monitoring around a given feature, we often frame it around delivery and developer velocity as much as about reliability. For example, we've enabled teams to move faster and with more confidence that their changes are not going to negatively impact users. As part of the scaling of our approach in our organization, we also need to accommodate for the immense scale of Google Maps, both in its feature set and user base, each of which continue to grow. Scaling this approach to all of our organization required thinking about long-term sustainability and maintenance. The user experience is always changing, and we need to ensure that automatic outage prevention and detection capabilities also evolve to ensure a high true positive rate. We don't want our change supervision and production alerting to create a drag on developer velocity. Being responsible for user journeys also introduces new challenges around identifying root causes. Unlike server-side SLOs, which point directly to the part of the stack which is experiencing a problem, responding to user experience issues requires an end-to-end view. This opens up questions around ownership. When there are many parts of the stack that are involved in a user experience, it's not clear who should respond. User-centricity is the future for reliability-focused teams. As reliable cloud infrastructure becomes table stakes across the industry, there's an opportunity for reliability-focused teams to deliver even higher business impact by focusing on the user. This trend is visible in the development of open standards like OpenTelemetry, which are building out real user monitoring. Beyond existing user experiences, there are new challenges with AI-powered systems. Unlike other types of user experiences, AI-powered features can be non-deterministic or respond differently in response to the same prompt, complicating debugging. AI-powered features also require new approaches to telemetry that fully capture bad experiences. I'll end my talk with a call to action. There is tremendous opportunity in this space, not only for you personally, but for the industry as a whole. The pivot towards user-centric reliability is currently transforming how businesses think about their reliability investments. By driving a shift to user-focused reliability in your organization, you'll own a part of defining this future. Thank you.